she's currently at the University of Waterloo at the Institute for Quantum Computing, and she's working at Graham Smith. And she used to, but she just did, well, you finished your PhD maybe a few months ago.
Yes.
With Matthias Christandl at the University of Copenhagen, and well, she's been working a lot on channels, and this is what she's going to talk about.
Yes. Paula? Thank you. Is the microphone on? I guess. I hope. Yeah. Thanks for having me here, and thanks for the introduction. This is indeed some joint work that I did partially during my PhD with Matthias Christandl in Copenhagen, Alexander Müller-Hermes in Oslo, and Marco Tomamichel in Singapore, about how powerful entanglement assistance can or cannot be in communication. So I'll just get, if it could skip, that would be great. I guess I didn't select the right thing. Okay, yes, right. Before we get started, I'm going to explain what I'm talking about when I'm talking about communication. So even in the classical sense, there's a lot of people working actively on how to communicate. And the general setup is that there is some sender that encodes an information you would like to send. There's some transmission that transmits the information, for example, via a wire or some wireless communication. And then there's a receiver who tries to decode the information as accurately as possible. And in classical communication, because you can copy bits, it's clear that maybe if you have a wire that corrupts your information with some probability p, it's better to send it just many times and do a majority vote on your outputs so that you can decode the information pretty well. So your situation is that you want some combination of encoding and decoding procedure so that what you guess for the message, the x prime, will be equal to the x with a probability that approaches 1. And you want that your comparison between how many message bits you send and how many channel uses you need is bigger than 0 in the limit. I mean, if you're sending just what I just said, a repetition code, so you just send infinitely many times, your probability by majority vote will go to 0, but also your rate will go to 0, actually, because you're just sending one bit n times if you're just copying 0, 0, 0, 0. So that is not such a good trade-off. But there exist better encoders and decoders, and in principle, maybe there exists some where you can have a non-zero rate. And this is indeed the case. If you have such a rate, that's called the achievable rate by this communication scheme. So this is dependent on the particular encoder and decoder. And the maximum achievable rate is if you take the very best encoder and decoder, so it's an optimization problem. And this is called the capacity of the channel T. So the channel T describes how your information is corrupted along the way, and its capacity is a number that tells you how good a given channel transmits information. So this was all classical. This was a difficult optimization problem with really big encoding and decoding operations. But luckily, it's actually proven that it's equal to this quantity here, which is the mutual information between the encoded probability distribution over your messages and what that channel puts out. So this means that instead of caring about what the encoder and decoder look like in particular, you can only care about what kind of probability distribution you can produce to put into the channel. And this already gives you some entropic quantity that nicely characterizes how well this channel transmits information. So it's basically just an entropic relation that in particular very nicely contains that if your channel output is completely independent of the input, so if this entropy is just the sum of these entropies, then your capacity to transmit information is 0. So that makes total sense, because if your channel output is completely independent of what you put in, you cannot transmit information. Right. So that is, from classical information theory, the seminal result, let's say, yes? Oh, yeah, sorry, that should be, yes. Yes, sorry, that should be the input. Yeah. Yes, and then there's also this equivalent form in terms of the Kullback-Leibler divergence. We're going to come back to that later a little bit. Right. And if you make stuff quantum, it's not entirely obvious that there is one particular communication scenario that is completely analogous to the classical scenario, because you can make different parts of this thing quantum, and under the different assumptions, different capacities come out. So in particular, your first assumption could be that your wire is quantum. Could be quantum just because it's very small and maybe cold, and just quantum effects appearing in your transmission. And in this situation, you're still trying to optimize your encoding of some message into a quantum state. The quantum state is transmitted over copies of the channel, which is now a CPTP map. And your decoding maps a quantum state to a guess of a classical message. And this would be transmitting a classical message via a quantum channel. Right. So that's one of the generalizations, and already it's a weird one. Because as it turns out, you can also, okay, this is also an optimization problem in the similar way as the one before, over quantum maps now, but you can also find an entropic formula that describes how well a channel can do this nicely enough, but it already has a very weird quantum phenomenon of non-additivity in this case. So here there's a mutual information that looks similar to the one before, right? It's just a function of the eigenvalues of the state. And here we're maximizing over quantum classical states instead of the input probability distribution. So we're maximizing a CQ state that goes into the channel in one part. And the actual capacity is only given by this regularized formula. So you have a 1 over n and tensor products, because tensor products of the channel are super additive. So this quantity, if you take T tensor 2, you can transmit more information. This was a conjecture for a long time that this is actually equal to each other, but it's not true. And already a weird quantum phenomenon that means that this capacity doesn't really work very analogously to the classical case. And yes, we're going to we're going to talk about how some of these capacities compare. So maybe try and keep in mind this mutual information with the CQ state. Then there's another quantum phenomenon. So now you could think that your wire being quantum and being subject to quantum noise could be problematic for you. But sometimes quantum is also nice. For example, if there is quantum entanglement, which can be used for communication. So if you allow your sender and receiver to have some pre-shared entanglement, maybe even unlimited entanglement just for the fun of it, then you have something that is called the entanglement-assisted capacity of the channel. And now this is actually equal to a mutual information where you're maximizing over all the states. So that looks a little bit more like an actual quantum analog of the classical case, because you're not restricting how these states look, but somehow you need entanglement assistance to get a formula like this. The state. So this is a state on two systems, and one system is going into T, and one is going into the identity. And then T is mapping from A to B. So yeah, A prime is the system that doesn't go into T. A is the system that goes into T. So it's a mutual information after T is applied with the other half of the input. Yes? So that's also a mutual information quantity, and this one is additive. That is also cool. And the question that arises, sort of, is how to compare these two capacities. So this is what this talk is going to be about. And we're going to start with a very simple example, superdense coding, which I assume you're all familiar with, probably. But in superdense coding, we're trying to transmit classical information by using a quantum channel. And the quantum channel is just the identity, so a noiseless channel on a qubit. And we know that if there is an identity channel, we can transmit, and there's no entanglement assistance, we can transmit exactly 1 bit. In this case, the Holevo quantity and the classical capacity are also equal. And if we have entanglement assistance, we can transmit 2 classical bits. We know exactly how this strategy works with Pauli application. And there is one, yes, and now, obviously, since we're maximizing over 2 different things, it's clear that the classical capacity or the Holevo quantity will be smaller than the entanglement-assisted capacity. So if you take their quotient, it's going to be lower bounded by 1, because you're just maximizing over a bigger set for this one. And in this case, it's going to be equal to 2, this quotient. So that is what some people take to imply that entanglement can help you send classical information, can help you send bits, and it can improve your rate, your achievable rates. And the question that we're asking is kind of how much can it improve these rates? So the identity channel is actually sort of a bad example. You could think that that's the best channel to look at, but actually the noisier the better, because we're just looking at how the entanglement improves the communication rate. So for very noisy channels, this improvement is much bigger. And there has been, even in the very first paper on entanglement-assisted communication, they computed the capacity for these channels, which is comparatively easy because it's a pretty simple description, and we know kind of what kind of probability, what kind of states maximize the formulas here. So here it's a simpler, maybe, formula than this maximization over mutual informations that only depends on P, and then you can calculate this quotient at each point. And now I've plotted here for different dimensions the depolarizing channel. And you see already that for qubits, t equal 2, the number is 3. And you can even prove analytically that it's, so this was numerics, but you can prove analytically that it's 3. So 3 is bigger than 2. And this is exactly at the point where the depolarizing parameter is 1, which is where the channel is the noisiest, because it's outputting every time just the maximally mixed state, right? So it's outputting something independent of the input, and the capacity is approaching 0. And for the other dimensions, you also see like this. So it could, in principle, go to infinity, and you can analytically prove that it approaches this function. So it becomes 2d plus 2 for the output dimension. So for finite output dimension, you can indeed prove that this quotient is bounded. And yeah, in the original paper, they took this to mean that if you let d go to infinity, it's not bounded. So they were like, entanglement is great, which I agree, but in principle, for finite dimensions, it's the greatness is limited, let's say. And in this paper, they also conjecture that the same bound holds for all channels. And that is sort of the last time anyone heard of it, because it's pretty hard to prove in general, because these functions, they look very confusing and complicated, and if you don't have much information about the channels, you will run into problems very easily. So the first caveat that I'm going to say is that we're going to be looking at the Holevo quantity. We're not going to care about the additivity problem, because this will be the entanglement-assisted capacity divided by CH is already an upper bound on CEA divided by C, because the Holevo capacity is a lower bound, right? And that means that we're just comparing these two mutual informations where the maximization goes over different things and trying to lower bound one of them and upper bound the other one. So some of the strategies that you can immediately think of, okay, and the problem is somehow that you want to upper bound and lower bound them by something that is the same function or proportional to the same thing. So in the same way, you can have some easy upper bounds on this because the entropy has an upper bound, but you cannot simultaneously have a lower bound that is, I mean, if you're upper bounding this by log d, then this can still go to 0 very horribly, and it can still become infinity. So you kind of need some sort of for all channels, a lower bound on this and an upper bound on this. And one thing, for example, is also that you could think, right, this is a CQ state. So it's basically like, you can see it as applying a measurement after the channel on this side. So that way you can get a lower bound on this by data processing inequalities as well, but you cannot get an upper bound. So there's some, there's some pitfalls in the ways that you would maybe approach this, so that many easy strategies do not work. But I'm just gonna it's back? Okay. Back to the slideshow. And in this talk, I'm going to talk you through how we proved for many channels that it is indeed bounded. Oh, and this is not where I wanted to say that. This is here. By some function that only depends on the output dimension and some weird thing. But in principle, it means that this is a finite bound for all channels that fit into a huge class of channels. And the function looks something like this, which is worse than the conjectured function, but at least it's something that is not infinity. And the proof of that is actually not too difficult, so I am actually going to sketch it in this talk. And I think all of the tools somehow were already kind of available in the literature or in implicit, I don't know, intuition or something, but they were not put together in this way. So I think the main contribution, honestly, is trying to make sense of all of that. Maybe the only thing that that is slightly new is an upper bound on the mutual information that we got. But the first thing we have to realize here is that the quotient can only diverge where the capacities go to 0. Because if you have a lower bound on the classical capacity, then your upper bound on the entropy means that you have an upper bound on the quotient, because you're just going to have log d times log d over epsilon as an upper bound. And the problems only appear when this epsilon goes to 0. And this is the case in some very particular examples, namely the so-called replacer channels that replace your state with a different state anytime, regardless of what you put in. They always output a state sigma. And these channels are the channels that completely destroy the information, because they will always output something that is completely independent of the input. And it's an if and only if, which is important, that the classical capacity is 0, if and only if the channel is a replacer channel. And in this case, the entanglement-assisted capacity is also 0. It's also a mutual information, so destroying the information means that it's also 0 in these points. So what we're looking for is channels approaching this replacer channel and how both of these functions behave around there, because that's where we could be looking for a counterexample or a proof. Okay, and then the next step is to realize that these mutual informations also have nice properties that you can use to describe their channel image. So this is a alternative version of writing this mutual information that is maximized over CQ states via a relative entropy, where you have some, well, basically you're taking the image of your channel and calculating its geometric center with regards to relative entropy. So there's one single unique little state sigma that is in the center of your channel image, and you can view your capacity as a distance from the sigma, some sort of distance, like relative entropy distance. And this means that you can, since the sigma is a unique thing, you can see a replacer channel that always outputs the sigma, so you have a distance that's of sorts between the channel and a replacer channel, a particular one. So now we, yes. And then for the entanglement, so this was known for the classical capacity, and for the entanglement-assisted capacity, a similar thing is true, with instead taking the channel image of identity tensor T. So it's a bigger space, and you still have, basically by rewriting all the entropies in here and then making some calculations that show you that you can exchange infimum and supremum or something, you can show that this is also equal to this thing, where now we're taking a relative entropy distance between identity T and identity replacer channel with some other replacer state. So the thing that minimizes this expression doesn't necessarily have to be the same thing as that thing that minimizes this expression, and we have examples where they are not the same. I think it's also an interesting question if we can find some if and only if conditions or something where they are the same, but we currently cannot. But the main maybe takeaway now from this is how we're going to use this in the proof, which is by going to the vicinity of replacer channels and then expanding these quantities around them. So we already kind of treat this like a distance from the, so the channel capacity can be treated sort of like a distance from the replacer channel, and now we're going to go into a ball around the replacer channel and prove that basically the convexity of these functions means that they are similar. And the way that this works is, first of all, we took an infimum over this sigma, so we can, without pain, because we're just upper bounding the entanglement-assisted capacity, replace that with the sigma from the classical capacity. And then here's the maybe difficult part. Because the relative entropy is a convex function, we're going to use a Taylor expansion, and since it's 0 in the replacer channel, we're going to upper bound it just by the second derivative. So the first derivative is 0, the actual function value is 0, and the second derivative is upper bounded by this thing. And you get some thing that is quadratic in the trace distance, in the maximized trace distance. And this is a well-known lower bound for relative entropy. Okay, well, what this thing has, maybe that the relative entropy doesn't have or isn't known to have, is that we know how to deal with this enlarged space here, because the trace distance has something that is called stabilization property, where you can get rid of this extra space by getting an extra dimension factor. So that's why we have two extra d's here from 3 to 5, because we're using the stabilization property that we only know in the case of these actually proper distances. And this, then without the identity, we're just having a distance between T and the replacer channel for the classical capacity. This is a well-known bound on the relative entropy, which is now equal to the classical, or the Holivo capacity, I should write, sorry. Yes, so that are all the steps that are necessary to prove that the entanglement-assisted capacity is upper bounded by some function of D times the classical capacity. So there's a limit. Yeah.
But the denominator there also depends on the calculated the Holivo capacity.
Yes, so that is exactly maybe the cases. Okay, right. I said almost all channels, and this is kind of where the almost all channels appears, because this sigma is the minimum eigenvalue of the center of the channel. So we need to have that the center of the channel has some rank condition. It actually has to be in the middle of the channel image. And in some sense, I mean, now I talked before about the balls of around replacer channel in the space of channels. For two convex functions, we have that both of them are kind of like convex, lying above each other, as long as this minimum is in the middle, in the center of the, like not on the edge of the ball. So the things for which this thing doesn't hold or for which this thing is a useless bound, let's say, is if the minimum eigenvalue is going to 0, which means that we're going towards a channel that has changes rank. The channel image changes rank along the way. So one example of this would be the amplitude damping channel that goes towards the 0, 0 state, which means that the end state, that is the replacer state it goes to, and that is a pure state. But before, you're going towards it via states with full rank. And this is one of the channels for which this bound doesn't hold. For the amplitude damping channel, though, there's another result, actually, where they bound it. And in that case, the bound is 4 qubits. 4 is bigger than 3, but let's not talk about it. and there they use something completely different, let's say. There they are actually also, because amplitude damping is also a few parameters, and you can prove that the maximizing ensemble will be, like, you have knowledge about what it would be. So there you can actually expand it as well and compare the leading order terms and see that it analytically is proven to be upper bounded by 4. And there's also known examples in the qubit case where it can even be 5.1. So the depolarizing channel that I showed is not even the maximum in the qubit thing, but there's just, yeah. But I just said that in order to say that the amplitude damping channel is also not the maximum in the qubit case. So the one that is 5.1 is actually also covered by the strategy. So maybe it's not too horrible to leave out some of these channels that lie really on the edge of the channel set. So probably even if you have channels that map to a subspace of this, as long as it has full rank in the subspace and you don't go via a sequence where it changes rank, you're still fine. But for the real edge case where you're going really to the point where the rank becomes 1, we don't know how to deal with this. / this bound is not helpful. Right. Yes. So that is maybe how we can arrive at an upper bound in terms of this function between entanglement-assisted capacity and classical capacity. And this is already kind of the main result of the talk for single channel coding. And there's, yeah, as I said, there's some cases that aren't covered by this. And we maybe have some techniques that work for this, but most channels should be in the center of their own. Okay, most channels should have a geometric center of their image set that is inside the set. So that is why I said almost all channels, and the cases that aren't covered, they require some different techniques. Right, but this was all single channel coding, and now I'm going to talk about a different communication model in which the whole thing does not hold. So the communication models that I explained in the beginning, they are all communication via some channel and n times that channel. So you have an equivalence of sorts between using a channel n times and having n parallel copies of this channel. But people have also looked at more complicated communication models that don't have necessarily such nice entropic formulas. And one of them is this thing that is called communication with system uncertainty. So now I'm imagining a situation where I have a sender and a receiver, and they're connected by a wire, but maybe they don't know exactly the temperature of the wire. They know some range, perhaps, or some discrete steps that it could be at, but they don't know it exactly. And if they don't know it, they only have a set of channels that their channel could be from, and not exactly the actual model of the channel. So then the goal is to communicate via all the channels in the set sort of decently, and this is called the compound capacity of the set of channels. So in the case of it being the same channel over and over again, so again, still n copies of a channel, but you just don't know exactly which one, the best thing you can do is sort of communicate for the worst of them. So you take a minimum, and you just check which channel is the worst of them, and design a coding scheme for that, and it turns out to work decently well for the rest. And you can also have a situation So that's in classical communication. And you can also have a situation where the channel could vary through time. So maybe you're sending multiple times and it will be something from the set, but you don't know why, because the temperature changes or something. This is called arbitrarily varying channel. And there you also have complicated, yes? Yeah?
Just to see if I understood. So you have a channel that could be chosen by a list of channels, but it is, once it's chosen, it is the same answer, right? And you're saying about the worst case.
Yeah, because the situation is that the sender and the receiver do not know which channel was chosen.
Yes.
Yeah.
But the figure of merit is like the worst case.
Yeah. Okay. Okay, and the same sort of thing you can also consider in the quantum case, of course, where you have some set of quantum channels, and you introduce an entanglement-assisted version and a classical version of these compound channel capacities. They also have nice formulas, and we're going to care about a very particular one now, which is a compound capacity where we're allowing for an extra input state. So in this case, we have a channel now mapping from AS to B. So we're not going from A to B anymore. The T is now a bigger T. And you can define some compound channel set by a set of states that can be input into one of the systems. So you could even take all the states, and the only restriction in this case that I'm putting here is that this sigma is in tensor product form, because I'm putting one sigma and the same sigma into each channel. So this would correspond to a compound scenario where I'm jamming the input of each channel in the same way. And people sometimes call this also communication in the presence of a jammer or an adversary. I said it now in saying something about the environment and temperature, but in principle you could have someone who controls this and tries to disrupt your communication as much as possible. So that's why sometimes people call this also adversarial. But here for this situation you also have the same formulas as for the classical case, where you can still code for the worst case scenario, right? And this picture in general on purpose does not have sigma in tensor product form, because what you could also be thinking about is a sigma that is not tensor product in the n channel copies. So this was first done in 2018 by people in Munich. They called this fully quantum arbitrarily varying channel. lots of letters. But the situation that you're imagining now is that someone can know or after you encode your state, someone can jam parts of the inputs by a really big state. So you have still n copies of channels that take A and S as input systems, but the subsequent channel uses are sort of adaptively changed by your adversary or by this environment state. So this is not exactly the traditional coding scenario anymore, because it's not IID, and you don't have just independent channel copies n times or n uses and it's all equivalent, but instead you have this thing that they call fully quantum arbitrarily varying channels, in order to see how well you can communicate in the presence of such a correlated environment state. So another way to view this is also, if you had an adversary or an environment, how much can it disrupt your communication, depending on what kind of power you give to it. If you restrict it to be tensor power states, then it can restrict your communication to the compound capacity, and if you give it the power to be entangled, it allows you this communication. So this is obviously smaller than the compound capacity, but as it turns out...
So how is it obviously? It's obviously not larger, but why would it be obviously smaller?
I mean, okay. I think what I'm saying is that it's obviously not larger. So it's a more restricted scenario. I didn't say if they are equal or not. Actually, I guess in fact, we will show that they are sort of equal as long as you restrict your sigma's dimension, so how much correlation it can have. But yes. Yeah, it's only one way of the inequality. Yes. So yeah, maybe that was already kind of the answer, being that even if you give a lot of power to your environment or adversarial state to manipulate these channel copies, in fact, you cannot reduce the communication by that much because it will be equal to this compound channel capacity. So in the entanglement-assisted case, it will actually be equal. You can show an upper bound and lower bound. Basically, as long as your sigma's local dimension is not infinity. And for the classical case, you have this very curious tautology result, which shows you that it's equal, that's either equal to the compound capacity or it's zero. And I wrote this in a, yeah, so if it's not zero, it's not, yeah, anyway, if it's zero, it's zero. That is what this is saying, right? But there are known cases where the compound capacity is non-zero and the fully quantum arbitrarily varying channel capacity is zero, that emerge already from sort of classical communication shenanigans. And the question, okay, if we could have a nicer if and else condition here, is an open question that I don't think anyone really knows currently, because in the classical, completely classical case, there is a symmetry condition on the channels for which the, yeah, so if the channel fulfills some symmetry condition, the capacity is zero, and otherwise it's equal to the compound capacity. But here there are more cases, more known cases of channels that have a compound capacity bigger than zero and a classical capacity that is equal to zero, and a fully quantum arbitrarily varying capacity that is equal to zero. And we don't have a good if and only if condition on the channel. And luckily, already knowing that there exist some channels and some examples of these channels is enough to knowing that there exists a counterexample, because we do not have the same thing going on for the entanglement-assisted capacity. So we know that there exists channel where there exists at least one channel, there exist several channels where this thing is zero, while this thing is lower bounded by the compound capacity, and therefore not zero. And I mean, so what we definitely have in this weird communication scenario that is not single channel coding is that we have examples where this quotient diverges. And somehow this is very intimately related to the fact that you can use entanglement to generate randomness. Because in the classical scenario, or the channels that have zero fully quantum arbitrarily varying capacity and non-zero compound classical capacity, for example, some of them are the ones that fulfill the symmetry condition, which means that they act sort of like, with some probability, they transmit the state, and with some probability, they flip the subsystems corresponding to sigma and rho. So you get some confusability that you didn't have before, and this lower bounds your probability of communicating, and therefore you have a zero capacity. And you can counteract this to some degree by having access to shared randomness, and entanglement is kind of like access to shared randomness. So that's a very high level, not very precise way of describing these examples that we know, but there's also plenty of examples where we know that they maybe have a similar relation, but they aren't described as these symmetric channels with the symmetry condition. Yes. That's already kind of the end of my talk, because I didn't want to go through the proof for the fully quantum arbitrarily varying things, because it's not as nice as the other proof. But in total, I mean, I just talked a lot about this conjecture that entanglement assisted capacity divided by classical capacity is not infinity, which you can translate to say that entanglement cannot improve your communication rates infinitely much as long as the channel dimension, output dimension, is bounded. And for single channel coding, we showed that it holds for almost all channels, and it's kind of emerging sort of nicely from a picture of the channel image and the convexity of the functions you're looking at. And of course, open questions are whether we can improve this bound, because we have a dB to the 5. So we already actually kind of know how to improve it to a dB to the 4, I think. But it's still not what the conjecture is, which is linear in D. And of course, the question is, can we lift from almost all to all? But there are some big hurdles in the way, because calculating for these channels, none of the techniques that you could think of seem to work. And for a more weird communication model, it's not more general exactly, because there's this added assumption of this extra jammer that controls part of the input state. But for this sort of communication model where you're allowing someone to manipulate part of your input, there exist counterexamples. Characterizing these counterexamples is still an open question, so finding some if and only if condition for the thing I showed before. There's also this restriction of the environment dimension. This is because we're using a De Finetti theorem somewhere in the proof, and this is currently not easy to see how we would get out of that. It's even in both open in all the ways, so you could show that you can never communicate in a really fully quantum with infinite environment dimension model, or you could show that it's equal to the compound capacity. It's completely, both would be interesting, right? And right. And then the last thing that is also an open question is that there are some other models of communication where you could look on the restricted sets of channels or states in order to check the conjecture there. So there's also, for example, something that is called, that is an arbitrarily varying channel in quantum without having entanglement between the between the channel uses. So there you can still probably have phenomena that are similar to this fully quantum arbitrarily varying thing that I talked about, but I didn't really look at it yet. But that, I think, that is all I wanted to say. So thank you for your attention.
Nice talk. So, any questions?
Thanks for the talk. It's very good. I have a question, like this entanglement assistance. Do you have so this is arbitrary?
There is a, okay, I now talked about it without specifying, but in principle there is a proof that there is a limit on how much entanglement assistance you need. So there's some entropic relation also that shows you how your number of entangled states that you give to the sender and receiver scales with n. So there is some sort of bound on this, but for this it was not necessary to specify. I'm sorry, was that the question?
Yeah. So
okay.
If you have more entanglement, at some point it doesn't have.
Yeah.
Okay.
Yeah, exactly. I mean, this is for the single channel version. I'm actually not quite sure about the fully quantum arbitrarily varying, but yeah.
It's a very naive question. So somehow, assuming that you can use entanglement, you're assuming that either you have perfect memory, or you maybe have a channel, so you can create an entangled state, and you can. So on one side you have T, but on the other side you have the identity somehow. Right?
Yes.
So my naive question is, are there known bounds when also the entanglement you use is subject to noise, or
Yes.
you need to use the same T, or it's trivial?
No, there are bounds on this. Different versions of noisy entanglement. So if you still have a pure state after, so I'm imagining now that I'm distributing my entanglement and it's subject to noise on the way to the receiver. If the state is still pure, you can distill the entanglement back. And if it's mixed, there's also bounds on how well you can distill the entanglement back, you're using a really small fraction of the T for a classical communication. But yeah, there's also places where they compute the rate for that and noise restriction.
Connected to that, like if you have an entangled state that is kind of local, where there is a local model, is it still helpful? Or like do you have...
I guess bound entangled states. Maybe if you can use it still to generate some randomness, it would be helpful. I would guess in the fully quantum arbitrarily varying scenario for sure. In the single channel coding thing, I think you would want some sort of state you can distill entanglement from.
I think I understand very well the last scenario, no? When you consider that it's interacting with the environment, because what is exactly your model? You have like the model for the channel T, or not? You don't have, or you only have, what is the model exactly?
Okay. Yeah, I would say you have a model for the, so for a particular channel T that has two input systems, well, the thing that I did works for any channel T like that. So the model is not restricting very much the T, but I'm restricting the jamming input states to either tensor products or not tensor products. I mean, and for a div, it has a part that, yes. So you could, I guess, what I mean, also you could think of a situation where you have several depolarizing channels with different parameters P, and you have a state that just, like the environment is in some sort of classical state that just controls which one is being used. So that would be one example of a channel model like that, where the jammer controls, let's say, which channel exactly connects you. But you can think of any kind of T, I guess, as long as, well, no, you can think of any kind of T. Maybe it doesn't even have to be so that the sigma always makes it into a different channel, because you could have a compound set with just one channel and it would just be one single channel coding. But yeah, so I guess I'm thinking of this channel as some sort of channel that takes an input from the environment, and any kind of channel that maps from A to S, AS to B is valid in this.
The other thing is, anybody, because for cryptography, I'm not sure if the scenario that you presented is really the more general one, right? I mean, you imagine that the channel uses sequential, so it could be that the adversary is actually measuring this environment right afterwards and adapting depending. So you don't have really a joint state, right? I mean, you have like a strategy. No?
Yes, yeah. There is.
People consider this?
I don't actually think so. I think even this fully quantum arbitrarily varying model for capacity is from 2018, not too long ago. But you could think of more general things that adapt your channels along the way. I don't think, in quantum, I don't think much is known.
Can you think of situations, going back to normal capacity versus entanglement-assisted capacity? I imagine that if the channel is classical, it's simply a measurement of entanglement breaking channel. I can imagine in that case it doesn't help, but does it? Or am I wrong?
Yes, it does actually help, because there is some. So let me get this very right. So the set of entanglement breaking channels, right? It contains the CQ channels and the QC channels and the and some other channels, but there is a condition on when the okay, so sometimes the classical capacity will be exactly equal to the entanglement-assisted capacity. But this is not for all entanglement breaking channels. So there's some weird condition as well on actually the channel image that, that pinpoints when your entanglement-assisted capacity and the classical capacity are equal. But for example, a depolarizing channel for very high P is an entanglement breaking channel. So there's already an example where it's 3, basically. So in fact, the big violation, or not violation, the big upper bound that we know for qubits is an entanglement breaking channel. So I think in this case, you still are using that there is some classical correlation helping you.
For what kind of channels it doesn't help at all?
I think CQ channels. Yeah, I think CQ channels are in this if and only if condition, but or not if and only if, only an if, but not all entanglement breaking channels, but some subset of them, and there is some condition that was found out in one of the early papers when, so then we know that they are equal. So there's a condition for when they are actually equal. Yeah, there is a condition for when they are, when the quotient is 1, but it's not
Sufficient or necessarily sufficient?
sufficient.
So, any more questions?